So in this chapter, we're going to look at Taptweaks. Now, Taptweaks are the way we can commit the different scripts, the alternative script paths into the Taproot output. What is a Taptweak? Well, generally speaking, any data can be committed to a public key tweak, right? And this has some really nice properties that we will take advantage of. So for one, the public key that is tweaked remains spendable. The owner of the private key of the public key can spend the tweak public key as long as he or she has knowledge of the tweak. The signing of the tweak public key does not actually reveal the tweak either. The private key owner can later reveal the commitment without revealing the private key. So this way we can nicely commit different scripts to the public key point in a way that makes the in a way that allows it to be indistinguishable from any other public key on chain, unless the owner decides to reveal it. So if we look back at our overview, currently looking at the tweaked internal key. The tweak is how we commit data, or in a specific case of Taproot, how we commit the different tap script spending paths into a Taproot output. So the specific commitment scheme that we use for Taproot looks as follows. We have the version 1 witness program, which contains a 33-byte pub key. This is the Taproot pub key. Let's call it Q. And to obtain Q, we first take an internal public key, and we tweak that internal public key by a factor which is the hash of the public key and the commitment. In order to spend this Taproot public key, denoted Q here, we simply need to tweak our private key, which is the private key of the internal pub key P, by the same factor, which is the hash of the public key and the commitment. So I'd like to spend one slide to quickly talk about why we need this commitment scheme to be able to validly commit data to a public key. In a naive scheme, one might think that I can simply take the commitment and directly tweak the public key or the internal public key with that commitment, as I'm showing here. The problem with that is I can later on modify this commitment, this scalar C prime, and I can solve for a new valid private key, resulting in the same Taproot output Q. So this obviously means that this is not a valid commitment scheme. Instead, if I have the public key point and the commitment value inside this hash expression, you can see in this equation here, if I change the commitment here, I cannot solve for a new private key, thereby making this a strong commitment scheme that we use.